Okay, so welcome to Power Systems Protection. I'm doing Power Systems afterwards, so I get a little bit confused. I am Tony Afok. That's my name there, and it so happens I am the examiner for this course. I may not be doing everything. There may be people helping me with marking. I don't know yet, but I'll let you know about this. But I'm responsible for the course. I am the examiner. I will set the exam and I'll be marking. Now, a little bit about the course itself. The course is running for the second time. We ran it for the first time last year. We run it reasonably well. There were a little bit of delay with a couple of things, but this year it should be so much better because we're relying on the experience of last year. The course will run in a similar way to last year, except with some updates on certain technologies. The technology is moving relatively quickly, and I will be including some more up-to-date material this year, but still on the main topics. The topics remain the same, the educational objectives remain the same, but as I say, manufacturers of equipment are a little bit more clear now about what they are doing, so we will include that input from the manufacturers. So the importance of the course, the importance of the topic, of course, extremely important. Australia would spend millions, if not billions, on electricity supply equipment, which would be used by the service providers, transmission service providers, distribution service providers, by generators, but also in other areas of industry like mining, oil and gas, manufacturing, process control. In all those areas, in food processing, you would have electrical equipment that would need protection. So if you're spending billions of dollars getting equipment into the country, most of which now are not manufactured here, it used to be, but not anymore. Now we get them from overseas, from big companies like Siemens, ABB, Hitachi, etc. We get the equipment, lots of investment. Typically, you spend at least 5 to 10% of the money on protecting the equipment. It is a smart thing to do to protect your equipment. In protecting your equipment, you're of course protecting against damage, but you also have to bear in mind that if you go too far towards protection, then you may be affecting the security of supply. So if for every time you think there is a problem, you shut down the equipment and you isolate it, then you may not be supplying your customers. So you have to be very careful. You have to get it right. So there is a balance between what we call dependability of the protection system and the security of your protection system. You have to balance that. And then you can't afford errors. An error one way is a problem, an error the other way is also a problem. So you would see how we have features within the protection design that would give you a good balance between dependability and security. Okay, so with the course itself, what you will require as prerequisite would be your previous knowledge that you have built up from electrical technology, from electrical plant, and some of you may have done electricity supply systems. So the knowledge you have built doing those courses will help you with this one. Also, some of the knowledge you got from different areas may be helpful, maybe a little bit of maths, but not much. Apart from that, I suppose the most important background that you should have would be your circuit theory, especially your AC circuits theory. So you need to revise that. You need to make sure that you understand things like complex numbers and phasors. You of course have to understand your equipment as well. And the equipment that we are looking at typically would be transformers. So you have to understand your transformer theory. You have to understand your transmission line theory. And towards the end, you have to understand your generator modeling. I will make, of course, an effort to go through the previous theory that you would have seen and make sure that you have is reasonable understanding of that theory. We do rely on fundamental principles like Kirchhoff's current law, Kirchhoff's voltage law. We rely on your understanding, especially of basic electromagnetic theory. When I mention inductance, you should not just see a symbol of an inductance. You should, a whole several centuries of effort should come to your mind about how people ended up with a concept of inductance and the idea of flux and the idea of relationships between current and voltage for inductance, etc. So you have to understand the basics. And usually I start with the basics. So I might do that and make sure that you do have that before we go on to more complicated things. My style has always been trying to help you prepare for what's coming. I think that's being pragmatic and practical. And usually what comes is your first assignment, and then your second assignment, and then your exam. So I find myself preparing you for those. And whilst I'm preparing you for those, hopefully we meet the educational objectives. The assignments themselves, the exam, etc., they are just a means to an end. You're not here to just do assignments. You're here to do assignments so that you meet the educational objectives, so that you get a suitable background that will help you in the future in your profession. What you find is once you start working and your employer hopefully give you training, etc., you get maximum benefit out of what you do later if you have had a good experience when you do courses like power system protection. So you have to take it seriously now if you want to benefit later. If you don't take it seriously now and you say, well, all I want to do is pass and get a C, I don't care, then you're going to pay a price later. Later, what will happen is your employer would say, okay, I'll send you on this course that costs $1,000 a day, and you'll go to those courses, and by the time we reach 11 o'clock on Monday morning, everything will be above your head because you haven't had the right background. So we people, we get paid to give you the right background so that you can benefit later. However, it doesn't just depend on us. It depends, mostly actually, it depends on you. So bear that in mind. We don't want to kill you with work, obviously, but we expect you to do about 12 to 14 hours of solid work per week. And I mean solid work. where you're focused on this course. A lot of people don't focus as hard, and I don't focus as hard, so it tends to mean that I take a bit longer. So I have to put a bit more hours in. When we say 14 hours, that would 12 to 14, that's for an average student. An extremely good student with some background may take less than that. On the other hand, a student who is not as, I would not say not as good, sometimes your better students are the ones who take a little bit more time to understand. But once they understand deeply, and they are better than the students who have taken less time. So bearing all that in mind, we'll start by refreshing ourselves on some important points. Any questions so far? Okay. So the course itself, as far as assessment is concerned, is made up of 2 assignments. The 2 assignments add up to 30%. And a final exam, which is closed book, and it is 70%. My philosophy is that the exam is not there to stress you during those 2 hours that you are having exam. It is just a check that you have studied before. So if you studied before, you will be okay. You will have at least 2 sample exam papers, maybe 3. Last year I gave them 2, but this year you will have 2 plus last year's exam. So you would have an exact idea about the style and the kind of questions that will be asked. If there are questions that will be slightly different, because, as I say, technology is moving, so we try to keep up. And if there are questions on those slightly new topics, I will let you know, and I might give you a couple of questions there. Or you remind me, and I'll make sure it is there. An exam is never a surprise. I don't surprise people. The question you will see in the exam, you would say, oh, I've seen that before. But be very careful. It's a different question. It's not necessarily exactly the same question. I might have, there's a transformer that I've given you before in the sample exam, and it could have been a delta star transformer, maybe DY1 or DY11 or whatever. But in the exam, I might change that, and I might go like this. So I expect you to read carefully in the exam. Don't assume that I've given you the same question. So read the question. I can't, at the same time, make sure that it's not a surprise and give you a question that is different without the danger of you thinking it's the same question. Because I've seen that before, where people haven't read the question and give me an answer to a previous question because they didn't read it carefully. So whilst the question would be, as I say, I don't want to surprise you, but don't make the mistake. Read it. Read the question. Okay. So so that's about your assignments. With your assignments, I now give essentially different assignments to different people. And I do that by giving you a different set of numbers, a different set of parameters. And in most cases, it's not just a matter of plugging numbers in. By tweaking the numbers a little bit, you can come up with completely different decisions. And I do ask you to make decisions about how to protect equipment, what sort of settings you're going to use for relays. So by tweaking say the fault level a little bit, or the length of the line a little bit, or something like that, the decision you make is entirely different from what your colleagues or your fellow students would be coming up with, because they got different numbers, you got different numbers. Something I have to warn you against, and that's academic misconduct. I trust most people are okay. Indeed, I would say a good 90% of students, maybe more than 90% of students, behave. They know the importance of making their own personal effort and get their own personal reward and get personal satisfaction out of that. Behaving ethically is extremely important. If you don't wish to behave ethically, do not be an engineer. I don't know what you want to be, but do not be an engineer. When that bridge collapses and people die, or the transformer blows up and kill people, that's the price we pay for not being ethical. And we have, unfortunately, every semester, I have to deal with people being unethical. People going on the net, buying assignments. We have evidence of that. People going to their friends of last year and copying their assignment. There's nothing wrong with looking at last year's assignment and learning from it, but at the end of the day, you have to do your own work. So if you get caught, you're going to be fully dealt with according to the university regulations. And you can go and see what the regulations are for yourself. You just have to type in the search box, academic misconduct. Indeed, do it, because it's good to know that, it's good for you to know that we have a definition of what academic misconduct means and where the line is, and keep well away from that line. Do not cross that line. We have, as I say, people who do it, we catch them. And it's not good for the profession. We live within a community, we live and work within a community of engineers. We trust each other, and we expect ethical behavior. Come and see us. If you put a question on the study desk, and it will be answered. Give us a call. 50% earned honestly is so much better than 90% that was obtained by academic misconduct. And again, if that happens, there will be consequences. I've had people in my office coming, and I've had extremes. Those that come and deny completely that they didn't do it. We have strong evidence that they have. And they come and say, oh, didn't do it. And the evidence is there, they get punished. I've had others who have come to my office and said, yes, we did buy the assignment off the net. And they're very upset about it. Very upset about it. So upset that, they cry. You don't want to be in that situation. Do consult with your friends. There's nothing wrong with this. Indeed, we encourage you to share knowledge, to learn from each other. That's strongly encouraged. But there is a time when, if that assignment is an individual assignment, there's a time when you stop the interaction, the engagement with friends and other people, and you do your own work and you isolate yourself from everyone. Then you're sure that it is your own work. I had a guy on Friday, and he came up with an assignment that looks exactly like, 90% the same as an assignment that was given previously. And we tracked it, and we knew that this was a previous assignment, was previously marked. And he said, oh, it's my own, because I got the assignment and has changed a few words, so that assignment is mine. So that's how naive this particular person was. You don't do that. Of course, you can look at last year's assignment, but when you write your own, burn that other one. Put it in the bin. Don't look at it while you're doing yours, because if you do that, then it's going to look the same. And once it looks the same, we will be suspicious and we'll look deeper and you'll get caught. There are some who believe that we are so stupid that we would not remember that we've seen this assignment before. We do. We've been trained, in fact, by ourselves to recognize work that we've seen before. We definitely will say, oh, I've seen this 2 years ago. Looks the same. And then we go and search for that, and you get caught again. So be very careful. We don't want to. It wastes our time. It wastes your time, and also it affects the profession. Submission as per normal. I have used an online submission, so it's online submission by the due date. I never ever give more than 1 week extension. If you wish to get extension, you would have to have a good reason, and good reasons are typically of a personal nature or something to do with your work. However, it has to be documented. So if it's medical, we need documentation. If it's to do with your work, we need something from your supervisor. If it is something personal happening in the family, again, we need documentation. So it has to be documented. Maximum we give is 1 week. We never, ever, for whatever reason, give more than 1 week. That's because, of course, the results are published. The solutions are published after that, after about 1 week. Hopefully, you won't need any extension. With assignments, I tend to give a good amount of guidelines to do the assignments. Look at those guidelines, follow them, make sure you understand them, because again, as I say, the philosophy of the examination is to check whether you understood what you did before. So if you follow guidelines blindly, then you're playing with danger again. So you don't want to repeat the course. Last year, this course was really done really well, especially by external students, because a lot of them are already working in that area. So the number of high distinctions were quite high, number of A's were quite high on the external cohort, with the external cohort. With the on-campus cohort, and we did have a bigger class last year, it was they struggled a bit, but still most of them passed. There were a couple of failures, and there were a couple of supplementary examinations. But generally speaking, it was done well. With the people without experience or not working in industry, I wish they did a little bit better. There were more of B's and C's, whereas the people in industry were more A's and high distinction. Having said that, there were still people from industry who did not do so well. The reason for that would have been lack of theoretical background. So a lot of people in industry would be doing things on a routine basis, on a basis of following some instructions to do something without the theoretical background, and that can be a problem. So people who are external, be aware that we test you on the theory as well as the practical applications of things. Okay, so talking about theory then, let us spend the next half hour or so on the basics. I'll just shut the door. Now, with the basics, what would we consider as basics? I think the first point I will make is circuit modeling. So that's the basics. You have to understand circuit modeling. So how do we model circuits? And I'll do just the very, very basics here. We have, of course, 3 circuit elements. Well, let's make it 5. I'll tell you why 5 in a minute. So we have 5 circuit elements that we play with. Five circuit elements. And we organize them in different ways to achieve different things. And I think we are lucky as electrical engineers. Mechanical engineers would have something similar. But if you compare us with, say, people doing philosophy or people doing business management, it wouldn't be as clear-cut. For us, it's clear-cut, black and white. We have only 5 circuit elements. This is in no way to simplify engineering to that level. Engineering is more complicated. But circuit analysis is simple. We got only 5 things to worry about. Can you remember them? Yeah, okay, let's go through them. Resistor, inductor. Sorry, resistor, inductor.
Yeah,
conductor. Yeah. Capacitor, yeah. Voltage supply. Voltage source. I gave you a clue there. Voltage source. And? Current source. That's 5 things. Okay, 5 things. Again, we go through them. Resistance, inductance, capacitance, current source, voltage source. That's the beginning. Don't let anyone confuse you. That's the problem. I think a lot of people confuse a lot of people. But at the end of the day, these are the 5 things that you start with. You have to know where the beginning is, and that's the beginning. So those 5 things, they are 2 terminal elements, and you know their symbols. So that would be a voltage source. If it's DC or AC, we don't care. So that's a voltage source. Then we might be dealing with a current source, not normally drawn this way. So that's a current source. And you have a resistor. So sorry about my symbol there. So it could be that or that one. I use this one because it's a bit easier to draw and it's still acceptable. So that's a resistor. And then you have a capacitor. So that's the one there. And you have an inductor. And that's the one there. So that's electrical engineering. Now, you probably think, oh, boring, simple, but really ask yourself, do I really understand this? Do I understand this? Ask yourself that question. So let's go through them. As we go through them, just remember that we need to define the direction of current and the polarity of voltage. Note language. Language is very important. I said the direction of current. I say current through. I do not say direction of voltage. Voltage doesn't have direction. Voltage has polarity. Current has direction. So make sure you get the language right. Electrical engineering is a discipline. It's called a discipline. And discipline means you have to be disciplined. You have to be disciplined in the way you communicate your ideas about electrical engineering. And discipline means use the language correctly. I may make quite a few grammatical errors while I'm giving this lecture. and I hope I'm forgiven. However, if I say voltage through, then I hope I'm put in jail. Because this is like swearing. It is blasphemy. I should not say voltage through. It's voltage across. Current through. Current through is a bit tricky with capacitors, but we'll come to that. It's okay. So make sure you get the language right. And talking about language, you make sure you get your, as I say, your directions right. I'll start with resistor. So I'll draw that. I can afford different colors, so I'll draw that different color here. So the definition of the current direction and the voltage polarity is like that. In the old days, people used to use a plus and a minus, but we don't do that anymore. It's quite confusing. So with voltage, we have an arrow off the circuit, and the arrow means that the high potential is at the tip. Nominally, the high potential is at the tip, and the low potential is on the tail. With current, the direction of the current is shown by an arrow. So that's our definition then of direction and polarity for current and voltage. And we do the same thing for all our elements, like this. Sometimes I will insist on using lowercase rather than uppercase, and I'll let you know about this later on. And sometimes we use uppercase rather than lowercase. But I'll leave them as uppercase for the moment. Okay. Now, there is a difference between those three elements and those other ones. These elements here are so-called passive elements. Meaning they are not sources for a long time anyway. An inductor can behave as a source for a short time, but it's really not a long-term source in the sense that it's not relying on conversion of energy from chemical to electricity or from mechanical to electricity. If it does store energy, it's really electrical energy. So they are called passive elements, and you will notice a bit of a difference between your your nominal direction of current and your nominal polarity of voltage between passive elements and active elements. These are active elements, and active elements can give you electrical energy indefinitely. This means these things don't exist, but mathematically they never get discharged. They give you energy forever. So because of that, we call them active elements. And with the active elements, you will notice that the voltage polarity is like this, nominally, and the current is like this. So you can see the current is coming out of the high potential side of the element. This means that nominally this is a source, so it's supplying energy. Whereas with them, nominally they are passive. They are passive, and therefore nominally they absorb energy, and therefore we show them this way. So there is a subtle difference there that we understand. This one here would be current this way and voltage that way. Yep. So good. Now, as I say, we know we have 5 elements. We know what the symbols are. We know how we define the nominal directions for current and the nominal polarity for voltage. Note that I'm calling them nominal because at first you really don't know exactly what the direction is until you do some calculations. But it doesn't matter. If you got the nominal direction wrong, it will just come out as a negative number, and we don't care. Like this so-called source here, you could be assuming that it's giving you energy, but when you do your calculation, you may find, oh, it's not giving me energy. It's actually taking energy from the rest of the system. And that's fine. All it means is it's charging. And that can happen in a situation where you have batteries in the system. The batteries could at some point be giving you energy. At some other point, it may be absorbing energy. So don't worry at all if your defined direction is not the actual direction that you find later on. Okay, so 5 circuit elements, symbols, directions, and polarities. And the step after this is to draw their characteristics. So you have to be able to picture the characteristic, put it on a piece of paper, ensure that you know what's going on. I am, of course, assuming all the way here that you know what current is and you know what voltage is. Current, of course, is a flow of charges. Charges exist. You don't have to care why. You don't have to care about who created them. That's not our business. We know they exist. Charges exist. And there are two kinds, positive and negative. And they got some properties like first of all, everything have got charges in them. You got charges in you, and the floor has charges in them. The table has, so all atoms have got charges. Generally speaking, equal numbers of positive and negative, generally speaking. And for the flow of electricity, in metal especially, it's essentially a flow of negative charges. But in other material, there could be positive charges carrying the current as well. So the flow of charges is a flow of electricity. We measure charges in coulombs, and coulomb per second going through a cross-sectional area is what we call current. So we know what current is. And current is a through variable. Voltage, on the other hand, is a potential for current to flow. Most people understand that if they say, well, if I have a tank of water here, and then that's on a tower, and I have a pipe here that I can open or shut, like a valve that I can open or shut, then there's a potential for this water to flow. So there's no current, there's no current of water coming down this tank, but there's a potential for it to flow. So there is a potential difference between this height and that height, as far as the water is concerned. Now, similarly, with electricity, there could be a potential for electricity to flow. Like you could have charged a capacitor like this with a lot of positive charges here and negative charges there. So there's a potential for electrons, if you like, to go from here to there because they are attracted to there. There's an insulator there, so there's a potential. And that potential is measured in volts, in a certain number of volts. So that's potential or voltage. So we understand what they mean, what current means, what potential difference means. If you don't understand that, let me know. I've got some notes of my own that I've written. I can send that to you, which I believe, of course, is the best set of notes on definition of currents and voltage. But you may not think that, but I think they are. So, but there will be other people who would have done the same thing, and I can point to them, or you can find them yourself. There would be good people on YouTube who would explain what voltage is and what current is. Yeah?
Talking about conventional direction current flow here as opposed to the American electron flow.
Yes, there's absolutely no confusion. I mean, one should not believe that this is so strange at all. When you think of current, you think of positive charges going along the direction of the current. But that's mathematically equivalent to electrons going the other way. So you don't have to worry about it. You don't have to answer the question, what's carrying the current? You don't care. In fact, you should not care. Because when you care, it starts to get confusing. You do all your work without knowing that it is electrons that's flowing. Because it could be. It could be positive charges that's flowing equally. It could be. So you don't have to worry about it. Power is voltage times current, giving you positive power, provided it's like this. Positive power coming out of the source, positive power being absorbed by your passive elements. So you don't really have to worry about it. Anyway, so we continue with this. And the key word here, although maybe people don't say it that way, there's a single word, and that single word is relationship. Right? It's relationship. So we know what current is. We know what voltage is. If you don't know, please let me know. And as I say, I will send you the set of notes, about 20 pages, that takes it from the beginning. I don't start from the beginning because this is supposedly final year course. But we are not too far from the beginning. You never venture too far from the beginning anyway, because we relate everything to fundamental principles. But if you don't know what current is, if you can't relate it to the existence of charges, and if you don't know what voltage is and cannot relate it to the idea of potential, and if you really want to go back, the idea of voltage has to do with the definition of work. You have to know what work means. If you don't know what work means, then you would not understand what voltage means. Voltage is related to work. If you don't know that, let me know. I've got a set of 20 pages that takes it back from what work is to what voltage is. Voltage is the amount of work you do if you take 1 coulomb of charge and do 1 joule of work as you take it from one point to the other. And if you've done 1 joule of work, then it means this point is 1 volt. There's 1 volt difference between this point and that point. So voltage is about doing work. It's defined as doing work from one point to the other. If you're doing no work, if in my hand here there's 1 coulomb, and with no effort I take 1 coulomb from here to there, I made absolutely no effort, then there's no voltage between this point and that point. On the other hand, if I have 1 coulomb there, and I have to really make an effort to get that 1 coulomb from here to there, then there is a potential difference between those 2 points. And the amount of potential difference will be proportional to the voltage between those 2 points. Now again, that's fully described in a set of notes that I have, and if you do want this, let me know. Okay, I said the key word was relationships. So this here, I'll take the one that people would be more familiar with. So this here is, there's a voltage and there's a current. Now there is a relationship, and that relationship is, I tend to say that a picture is good, but for every picture there's an equation, at least for those cases, and we tend to plot V against I, and we give it a name. We say it's the VI characteristic. And the VI characteristic is like this. It's a straight line. Doesn't have to be, but for metallic devices anyway, metallic resistors, it's a straight line. And the gradient of this is what we call the resistance. So the resistance is equal to gradient and is equal to change of V divided by change of I. So that's your change of I there. and that's a change of V there. R equals gradient, that's a change of V there. So which is the gradient. So that's a characteristic, and a lot of people, of course, write this as V equal to IR. So that's a relationship, the relationship between voltage and current. And I said the key word is relationship. So that's got that particular element, it's got a, for itself, it's defined as a relationship, and that's the relationship between voltage and current. We see the picture, we see the equation, we know the name of the equation, and people call it Ohm's law. So we don't have to worry too much about that. So that's for this one. Now for those ones, so for all five that you see here, we've got relationships. Let's pick the voltage source. So for the voltage source, I'll take that away now. So for the voltage source, there is a relationship, and that's the relationship. So for voltage source, again, we plot V against I that way. And can anybody guess? This is the origin. So what would be the relationship for a voltage source? We just did the resistance, and it looked like this for a voltage source. Straight line, yes. Any more information? Yeah, that's right. Across the x-axis, you mean there. Let's say it was a 100-volt voltage source. 100-volt voltage source? Okay. All right. That's okay. Good attempt. Good attempt. Yeah. Mohammed, so what's the answer? Voltage source? Okay. So a voltage source is like that. Say it was a 100-volt voltage source. So voltage source of E volts. So you were right. It was aligned like that, but it depends. How far it is from the origin would relate to the voltage rating of that voltage source. So it was a higher voltage rating, it would be up there. A lower voltage rating, it would be down here. But the important thing here is that it's a straight line, dead horizontal, perfect voltage source. And I'll call it, I've never done this, so I'm doing something for the first time here. So that's a perfect voltage source. How about a practical voltage source? How would the characteristic look like? Practical, that's perfect, that's in heaven, exists in heaven. Wavy. A real one might look, it doesn't have to, but it might look like that. So that would be a practical voltage source. Because as you take current from it, the level of current, depending on the level of current, the voltage drops. Okay. Now let's get a bit practical. If I were to give you a perfect voltage source, what would you worry about? Yeah, that's right. If you have a perfect voltage source and you had a dead short, you will get infinite current. And why you worry about it? We do have short circuits, they happen. But why we worry about it? We will not be able to buy a fuse or a circuit breaker to protect that source. The reason is any fuse, any circuit breaker, they are rated for some particular fault current. So typically in practice, when you have to protect something, remember this is about protection. So the voltage sources or things that come close to a perfect voltage source, like your power point is fairly close to a constant voltage source. So hopefully somebody worried about what would happen if there was a short circuit there. Now when you worry about, and you should worry about, what would I do if there was a short circuit there, and you had a perfect voltage source, you find that you got a big problem on your hands, because the fault current would be infinite, and when you check with ABB or Siemens or Hitachi and ring them up and talk to them or send them an email and you say, my fault level is infinite, please provide me with a circuit breaker or a fuse to protect this voltage source. And they would say, don't have anything that we can provide you. So you will be stuck with this perfect voltage source without a way of protecting it. And if you do have one, please let me know. I will make sure I am not too close to you. So yes, mathematically we can talk about a perfect voltage source. In fact, in practice, you find that our friends, electronic designers, they do design things that are very close to being perfect voltage sources. They use feedback to control the voltage. However, it's never a perfect voltage source all the way. At some point, the voltage will drop, which is a good thing, which means that your fault level then is controlled. It's a finite value rather than infinite. Therefore, you can protect it. Okay, so that was a perfect voltage source. What you never ever do with a voltage source, of course, is you never short circuit it. But if it happens, you should have a protection for that. Okay, so I'll finish today with this, and we'll continue again. Now, I have a bit of a problem because on Wednesday, is your lecture on Wednesday at 10 or 11? 10 is tutorial. So this week then, we won't have that lecture or tutorial. We won't have that, partly because I'm away. But please watch the study desk. We will put something there on the study desk for you to look at. It could be a lecture. Okay. And also, as we finish this, my style is sort of lecture tutorials rather than tutorial lectures. So please do come to all our sessions. It is important. Try not to think of, oh, there will be a lecture that will be recorded, and therefore you don't come here, because then I will be talking to Sayed, who is not a very good student. Yes. Okay, thank you very much.